So, dear colleagues, it's time to start our meeting of Kharkiv Chemical Seminar. And today we have a guest from Düsseldorf, Heinrich Heine University of Düsseldorf. Professor Christoph Janiak studied chemistry at the Technical University of Berlin and the University of Oklahoma, United States. He obtained his PhD at the Technical University of Berlin in 1987, following to the postdoctoral stays at Cornell University and BASF in the polyolefin division. From 1991 to 1995, he carried out his habilitation at the Technical University of Berlin. He got tenure at University of Freiburg in 1998 as an associate professor for inorganic and analytical chemistry. In 2010, he moved to the University of Düsseldorf as full professor and chair for the nanopores and nanoscaled materials. His research interests include the properties and utilization of metal-organic frameworks, covalent triazine frameworks, and methyl nanoparticles. Christoph Janiak has co-authored over 700 research papers, books, and patents. And his H index is about 96. And he supervised 70 students for obtaining their PhD degree under his guidance. And dear Professor Janiak, floor is yours.
Okay, thank you, Valentin. Yeah, welcome everybody. I am very happy that you listened to my presentation. And the only one I know is certainly Valentin, because he had visited me last year here in Düsseldorf. And okay, the title of my presentation you see here in front of you is Metal Organic Frameworks, MOFs, as they are abbreviated, for water sorption for cycling heat transformation. So Valentin told me that you had also Professor Yagi as one of your lecturers, but still, maybe I can give you a very short introduction into MOFs, just in case somebody is listening who is not so familiar with this material class. Now, wait a minute, come on. Oh, it's not, okay, yeah, here we are. So MOFs are a class of porous materials. And most of you may be familiar with zeolites or silica gels as inorganic porous materials, which are frequently used as detergents in consumer products. So these inorganic materials are more on the hydrophilic side and hygroscopic. So and on the other side of the class of porous materials, you can envision, or you could see the active carbon materials, and nowadays also covalent organic frameworks. They are more hydrophobic, of course. And in between, because they are constructed from inorganic parts, namely metals, and organic linkers, are the inorganic-organic hybrids or metal organic frameworks. What sets the metal organic frameworks apart and is special to them is their defined identical pores, because they are crystalline materials. These are also just like zeolites, which are also crystalline, but silica gel and active carbon are not crystalline, but amorphous. So they have a larger variety or variability in their porosity and in their microstructures. And what is also important in MOFs is their designable properties, because the organic linker, which is built in here, enables the whole range of organic chemistry to use as a design function. So MOFs are largely micro and to some extent mesoporous materials. And in this way, they resemble the zeolites, which are also crystalline and microporous, but zeolites are only to a very limited extent designable in their surface structure and properties. So what is perhaps also important is this area of a range of porosity and surface area. For MOFs, you can say they lie in between 2,000 to 4,000 square meters per gram. And this is not even the record value here. There are MOFs which have much higher surface area. And the inorganic class of materials and the organic ones are only about 1,000 square meters per gram. So shown here is a traditional soccer field, and MOFs with their surface area of around 3,500 square meters per gram would cover half the area of a soccer field. So let me give you two examples of metal organic framework structures. The first one is so-called MIL 101. It's a chromium MOF based on a very simple terephthalate or benzene 1,4-dicarboxylate linker and chromium, of course. And the metal in these MOF structures come typically as clusters, or you will see in a minute also in infinite chains. So here in MIL 101, we have a trinuclear chromium cluster. The chromium atoms have a oxygen in their center, and then are additionally bridged by the carboxylate groups from the terephthalate linker. And in this case, there's also a sixth ligand here, which is either a water molecule shown in the structure or a hydroxido or fluorido group. And then overall, the whole structure is charge neutral. So these trinuclear clusters and the organic linkers, they combine to superstructures. In this case, it's a supertetrahedron, and the trinuclear clusters lie at the vertices of these supertetrahedra. And then two of these supertetrahedra are shown here joined at a common vertex. So from this, the whole porous network is then constructed, and shown here below is one of these pores which are now surrounded or constructed from these trinuclear clusters and the linkers in between. Now, this is already difficult to envision how this looks like in three-dimensional space. So what people then often do is they schematize or give a schematic impression of the three-dimensional structure by, for example, taking here the center of the supertetrahedra, which are shown in black dots, and then the connection between these centers as green lines. So this then is a schematic view of the 3D structure of MIL 101. It resembles to some extent the zeolites, which also have these porous networks. It doesn't matter if you get a full understanding here. It should just give you a brief impression that metal clusters are important in metal organic frameworks, plus the organic linkers, and the overall structure can be more or less be complicated. So let's get to a second example, and that is a little bit simpler. It's aluminum fumarate, and also called basolite A520, because BASF, or BASF, has first made this metal organic framework. So the building blocks are a little bit more simple: aluminum ions, the fumarate linker, and an hydroxyl group. And then you have here a chain of octahedrally coordinated aluminum atoms, and the octahedral coordination comes about by bridging hydroxide group and the bridging carboxylate groups from the linker. So this is an infinite chain or an infinite building unit, and these chains then are connected to each of these sites by the fumarate linkers, giving these almost square pores or channels, which are one-dimensional and extending throughout the porous network. So it's also a three-dimensional network. I should add that most of these metal organic frameworks are really three-dimensional porous networks. So these MOFs have a lot of so-called application-oriented properties. That means people investigate all kinds of applications they can think of. But what I mean by application-oriented, it's still in the laboratory scale or in a provisional application. So to the best of my knowledge, none of the application has really entered the industrial scale yet, or a consumer good. To briefly go through these selected applications here, porosity is of course at the core, and then a lot deals with the adsorption or desorption of gases. That includes gas storage, gas separation, And in my presentation, you will hear about water absorption for heat transformation. People also look in pollutant sequestration, drug storage, care about luminescence, magnetism, spin crossover, even go into microelectronic applications like conductivity or semiconductivity. Nonlinear optics could be built in because of a chirality, which is possible through the organic linker. And then also a large part of applications concern catalysis. Again, having the porous network here as the inherent property for only allowing certain gas molecules perhaps to enter and have then designed catalysis. So that is probably close again to zeolites, which are also frequently used, especially in the petroleum industry, for catalytic properties to modify the petroleum, the oil. So now comes the part of the water absorption and the heat transformation. So we step back from MOFs for a minute and ask ourselves, why should water absorption in MOFs be important, and what about the heat transformation because of the water absorption? So if you live in many parts of the world, they are not really often as comfortable as Central Europe is. And by that I mean that you have much hotter climate, both especially in the summer, together with higher humidity. So in many parts of the world, comfortable living requires some sort of air conditioning. So here is a residential building from a normal city in China. Of course, the city already has over 100 million inhabitants. And encircled by these red rectangles here are 1 or 2 conventional air conditioners. So that is only one side of this residential tower. There are 3 more sides. And in a typical city in China, having more than 1 million people living there, you have not just one, you have thousands of these typical 30-story high residential buildings. So if all of them have these air conditioning units here for their apartments, that translates into a high electricity consumption. And electricity is to a large extent still generated by fossil fuel burning. Okay, nuclear power is also a possibility, but especially countries like China or India really still rely on fossil fuel burning for electricity generation. And also in Europe, our summers get more and more hot. So also we need more air conditioning. So how can or what would we have alternatives if we don't want to stress our electric grid because of increasing conventional air conditioning, which runs on electricity? Now, we could certainly sweat, but it's unlikely we would be very happy with that. Or you remember a process which is used also in other technological devices already, or which also nature uses, namely the transformation of water from its liquid state to the gaseous state. And thereby, I do not mean boiling, I mean the evaporation of water at 25 degrees centigrade. Now, for water to become a gas from this liquid, it has to draw the heat of evaporation, which is 2,440 kilojoules per liter. And this is a large amount of energy, and that energy comes from the environment. So this heat of evaporation drawn from the environment then cools the environment. And actually, this is the process which nature uses as sweating, or which we know ourselves as sweating. So when we sweat, our body cools itself through the evaporation of the water from the surface of our skin. So sweating is a so-called evaporative cooling process. So 2 more cases where this process is even used today. So the first one may look primitive, because what you see here in this image is a marketplace in Africa, for example, probably in Africa. And here you see 3 earthenware pots. And this is not a single pot, but it's a pot in a pot. So there is an inner pot in the outer one, which you can see, and in between there is a layer of wet sand. So from this wet sand, the water evaporates through the outer pot, and in the very inner pot, there is some food then placed, and the evaporation of the water from the layer of wet sand cools or the inner pot because it draws the heat of evaporation from the inner pot. So this simple process works because in many parts of Africa, especially in the sub-Saharan belt, the air is very dry. So the air supplies the driving force for the water to evaporate. So down here, you see that already an older civilization that has been used. And today in countries of Africa and India and Pakistan, it is still used. So of course, you may say, we have modern technology of air conditioning. Why should we make use of such primitive devices? But let's go to a country which is probably definitely not considered primitive, namely Australia. So in Australia, you see many single-family homes which have a unit on their roof, shown here in an enlarged version, which looks like an air conditioning unit, but it's not. Instead, it's a simple sponge material which is continuously wetted with water, and when warm air from the outside is drawn through this sponge by a simple cooling fan, and because the air is dry at the same time when it's warm, the heat of evaporation of the water which is evaporated this way enables the air to cool. So from an outside air temperature of 40 degrees centigrade, you can get down to 26.5 degrees centigrade, for example, if the air has a low humidity of only 20%. So of course, it depends a lot on the outside air humidity, how effective this cooling process is. So if the air is already very humid, it is not very efficient anymore to cool the outside air. And here is a map actually on the United States. And such a simple evaporative cooling drawing warm, dry air through a sponge, a water-filled sponge, would only work in the western area of the United States, which is more dry, but not in the more humid eastern area of the United States. So it works in Australia, and I've met people there who say that they have some unit. It saves a lot of electricity because all you have to have is a fan, but you don't have to have a compressor unit like a conventional air conditioner has. All you have to keep in mind, you have to leave the windows a little bit open so that the air which is drawn in from the outside would also be able to escape again, and no humidity will build up in the inside of the house. So now what do you do then if you do not have dry enough air which drives the evaporation of water to generate cooling? So then we have to resort to some other driving force. And now we come back to our MOFs, or let's say to porous materials. Namely, a porous material can also absorb water into its pores and present a driving force for water to evaporate. And here's a simple device which has a water-filled flask, water at the bottom here, and a sorbent material in another flask. There's a manual valve which separates both of them. And once you open the valve, the infrared image to the right shows what happens. So this water-filled flask cools down. Actually, it doesn't take long, within less than a minute, to sub-0 degrees centigrade. And because of the heat of absorption, the sorbent-filled flask turns quite warm. Here it's about 40 degrees centigrade. So this is, of course, initially a one-time process. And in order to make it a technological interesting process, one has to turn it around. So how can we turn it around? So let's look at this working cycle first again, where water or another working fluid is drawn to evaporation by an active empty sorption material. So when heat of evaporation is drawn from the environment, generating cold, and heat of adsorption has to be dissipated to the environment. And thereby, this unit, which then is, let's say, alternative air conditioner, has to be regenerated by applying heat of desorption to the sorption material, releasing the water again, which has to be condensed to give the working fluid and then enter the working cycle. So this would be the regeneration cycle. And to that process, one would need only 1/3 of the electrical energy which is used or which is needed by a conventional air conditioner. Of course, you may ask, where does the heat of desorption come from? And here you can envision solar thermal energy for the regeneration, or from many industrial processes, you have often waste heat, which is below 100 degrees centigrade, or you can even take, let's say, power plants, which also have waste heat, be it nuclear power plants or conventional power plants, which are only given off to the environment without any further use. So heat is often available, especially if it's below 100 degrees centigrade, which can enter in this process here for the regeneration. So if you now think, that's interesting or fantastic, I can already show you here with these two devices that this process already is commercialized. So the commercialization so far uses silica gel or zeolite, and there are different capacity scales up to even 1,000 kilowatt. And some companies are listed here from USA, Japan, Germany, who manufacture devices like that, which use evaporative cooling or adsorption chilling as a means of regenerating cold. And all these devices run in this two-chamber system or two-cycle mode. One chamber is in the working cycle, and the other chamber is in the regeneration cycle. And you can switch between these two cycles in a few minute interval. So it's a very quick working and regeneration cycle. And I come to it later why it can be so quick. So here is actually a device in real life with a capacity of 70 kilowatts using the adsorbent silica gel. And this device shown here is combined with a solar collector field on the roof of the building, where the driving heat is now generated by solar thermal energy. Now, if you now realize that already exists and it works apparently, because companies can make money from it by selling it, you of course wonder, before I come to it, why MOFs would be interesting. Actually, you can also use this technology not only for generating cold, but also for dehumidification. So if humid air is drawn through this porous material, it absorbs water, and then dry air is exiting this cylinder here to the other side. And for regeneration, you have this cylinder turning constantly, and through this little quadrant or quarter here of this cycle or circle, hot or warm air is blown, and of course both air streams are fully separated, and then the warm air drives out the water from the porous material to regenerate the active absorbent material. So this, of course, has to do with the fact that humid air feels much more uncomfortable or feels already hotter automatically, because our body sweating doesn't function in humid air as efficient as it does in dry air. So another thing here on this technology, you of course may wonder, how long has this been discovered? And shown here in this little scale, it dates back over 100 or 200 years by now, actually, to Michael Faraday, who most of you know him from electrochemistry, who has shown that adsorption-based cooling can be achieved by having ammonia adsorbed in silver chloride. Actually, that's more like a chemisorption and not a physisorption, but be it the way it is. And then the commercialization also dates back to roughly 100 years by now, where a working pair of silica gel as the adsorbent and sulfur dioxide as the adsorbate was used by US railways before refrigeration became available for mobile applications. Now, this technology of evaporative cooling or adsorption chilling was then replaced by the compression systems because chlorofluorocarbons were a great working fluid in these compressors. And electricity for a long time was no problem. Until then, the 1970s, when the oil crisis hit and ozone depletion became an issue because that originated from chlorofluorocarbons and so on. And now in the 1990s, when companies in Japan re-commercialized this adsorption chilling technology using silica gel and water, and even developed their own adsorbents, as you will see in a minute, to be more effective than silica gel. So we actually came in this field through a MOF synthesis from water, and this MOF formula is not important for the moment here, had a lot of water molecules incorporated in the network. So here you see the water molecules in space-filling mode within the framework. And we realized that these water molecules could be removed and reabsorbed over 10 cycles. 4 of them are shown here, without loss of water uptake capacity. So by varying the temperature and the water partial pressure, the water is removed with increasing temperature and lowering the water partial pressure, and brought back in by lowering the temperature and increasing the water partial pressure. So now comes the problematic issue I have to point out. MOFs are not really initially or immediately evident for any use when water plays a role. For a long time, actually, that was neglected, that MOFs are rather water sensitive. It's no wonder, because MOFs are nothing else than three-dimensional coordination net compounds. And coordination chemistry is well aware that water is also a great ligand and can replace over time and through the large concentration the existing ligands in a coordination compound. And the same thing happens in many MOFs. So if MOFs are exposed to water or air, which carries water with it, for 3 days or also in an extended time, 2 months, many MOFs degrade. So if you see here the red squares or the hatched yellow squares, that means that the MOF is completely or partially destroyed. And for many of these exemplified MOFs here, you see these red or hatched yellow squares. There's only one MOF or a few who stick out. Important is here MIL101 because it is stable in many of these conditions which were applied here, and to some extent maybe also UIO66 and UIO67. So now I come actually to the question which I wanted to pose already, namely, why should MOFs play a role or should be of interest in this technology if this technology already works with silica gel and zeolite? And that answer to the question is given here. So silica gel and zeolite are not really very porous. So their uptake capacity of water per gram of material is below 0.2 gram per gram for silica gel and 0.3 gram per gram for zeolite. And understandably, the more water goes into an amount of adsorbent per cycle, the more efficient can the cycle be run. And MOFs, as I pointed out in the very beginning, have a higher porosity or higher pore volume than many of the classical porous materials. So MOFs in a single cycle can take up larger amount, or many MOFs or some MOFs can take up a larger amount of water per cycle. And so that makes the whole process much more economical. Now, we of course have to look at another aspect which is important. So one I just pointed out is the amount of water which is absorbed, and that should be, let's say above 0.3 gram per gram, or here it's kilogram per kilogram, but that is the same. So the existing materials, silica gel, or even modified zeolites or silica gel, which were developed by the company Mitsubishi, do not meet this target. Now, a second aspect is that this uptake should be in a more hydrophilic region. So we have a minimum water loading, and we have to also consider here the prerequisite of an ideal working range. And that is not at 0.0 here, where zeolites often have an uptake, but a little bit higher, and but not too high. So it should go from 0.05 to 0.35. This way, it is hydrophilic, but not too hydrophilic, and also not too hydrophobic. So, for example, you see here also active carbon shown, and active carbon is hydrophobic. So active carbon will only absorb water at a very high, or rather high, water relative pressure. And zeolites, as I noted, are quite hydrophilic, but the early water uptake also means that you have to put in a high energy, or a large amount of energy, for regeneration. So zeolites, to regenerate them, require quite high temperature, longer times, and or even high vacuum. And that is why the ideal working range is in this region, which I just pointed out, where then lower temperatures, faster regeneration times, and possibly no vacuum needs to be applied. So silica gel, because it's amorphous and has a quite large distribution of pores and pore sizes, will take up water over the whole range of water vapor pressure. And that is not really attractive, because if one works in this range here, there's only a small uptake over this range and not an S-shaped curve, which is advantageous, because when you can vary or work in a small window here and have the adsorption and desorption process by modifying the relative water vapor pressure. So in our work, once we have got started, we looked at prototypical MOFs, how they would perform in terms of loading lift, and then the stability, of course, was an important issue. So 3 MOFs stick out here. Mil 101 because of its high uptake, Mil 100 iron because it has also quite a high uptake, and aluminum fumarate, whose uptake is not so high anymore, but it's very stable. So there is no degradation, no loss of uptake capacity over 2 times 20 or overall 40 uptake cycles, which we measured, or uptake and desorption cycles. So all of them meet this 0.3 gram per gram target. And the other MOFs, which you also see here, either show a large degradation, or and then move below this target line. So Mil 101, I showed you the structure early on, has this highly porous network with a large surface area of up to 4,000 square meters per gram, and it can take up its own mass in water. So there is a loading of over 1 gram of water per gram of MOF. The only disadvantage is it's too hydrophobic. So the uptake occurs above 0.4 relative pressure of water, and that is above the threshold, which I noted, which would be 0.35. Otherwise, it has good stability, and which is not over the 40 cycles which we measured degraded. So I also pointed out that Mil-100 iron has a high uptake, and it takes up the 0.75 gram per gram. It's a little bit more hydrophilic, so the uptake already starts around 0.2 relative pressure, or even a little bit below. But it's not really a clear S-shaped curve. So the uptake occurs in 2 steps and extends over a quite large range. And what is perhaps more important, its cycle stability is not really very high. So already over 40 cycles, the degradation in surface area and also some other parameters is visible. So here you see the uptake, the blue curve, it goes down. And that means the MOF is slowly but surely decomposing. And for a technological application, one would have to have for a lifetime of 10 years, let's say something like 200,000 cycles, which the material would have to survive. So now let's come to aluminum fumarate, which I also introduced you with that structure in the very beginning. It has these infinite building units, and from this, these square channel networks were constructed. So this MOF has a good stability and decent uptake capacity of a little bit above 0.3 gram per gram. So that brought us also to the field of aluminum MOFs. And they are not maybe so common in much of the literature, but for applications, they are great because the stability of aluminum oxygen bonds is much higher than for many transition metals, maybe except for chromium and perhaps zirconium. But aluminum is certainly a very common metal. It's considered not poisonous and so on. So, and then with aluminum, you can combine a lot of similar dicarboxylate ligand, shown here as thiophene dicarboxylate, and they give you very similar three-dimensional network structures with these similar square channels. So this thiophene dicarboxylate has a very nice developed S-shaped uptake curve with a capacity above 0.3 gram per gram. And the uptake doesn't change much with temperature. And also the range where the uptake occurs is right in the region where it should occur, namely here about 0.3 gram per gram. Also, the stability here was tested not only for 40 cycles, but over 5,000 vapor sorption cycles, and from powder X-ray diffraction, which is an indicator of the crystallinity or the crystal structure of the MOF, you see there is no visible change in the powder X-ray diffractogram. That means the MOF is still stable after 5,000 cycles. The red diffractogram is the one before, and the black one is the simulated one from the single crystal structure determination. And after we had discovered, or together with other groups, that aluminum MOFs would be a great MOF, or would be great MOFs for this type of application, there are other MOFs which you could look here at, such as isophthalate, giving you again the same structure or very similar structure, and the uptake is also a little bit above 0.3 gram per gram. Changes a little bit with temperature, but otherwise has a nice S-shaped curve. And here the MOF could even be shown to be stable over 10,000 cycles, again judged by the powder X-ray diffractogram and also by the water uptake capacity. So also there's no loss of water uptake over 10,000 cycles. So we didn't do it for every MOF because the time to run 10,000 cycles is a little bit longer, as you can imagine, than simply just 40 cycles. So what is also nice about these aluminum MOFs is that there are so-called isoreticular MOFs. That means, as I had just shown to you, many of these aluminum MOFs have a very similar structure. So because of this very similar structure, you can partially replace one ligand in a MOF with another one. So you get two mixed linker MOFs, which keep the same structure as a monolinker MOF. So here we have aluminum of COW10H with isophthalate and the aluminum of Mil-160 with furane dicarboxylate. So the linkers have a similar bent topology, and you can replace partially the isophthalate linker with a furane dicarboxylate linker and vice versa, and keep the same aluminum MOF structure with these rectangle or these square channels. So in doing so, you fine-tune the water uptake curve. So in pink is shown here the neat pure or the COW10H MOF with the one linker only, and in brown is the MOF Mil-160 with a single linker. And now if we replace partially furane dicarboxylate with isophthalate, we become a little bit more hydrophobic, and from the other direction we become a little bit more hydrophilic. So these are 5 out of 10 modifications we have done with the mixed linker unit, and thereby this water uptake range can be adjusted. So it may seem like a little game and not really so relevant, but for the technological application, such fine-tuning is actually more relevant than one thinks. But that would be an engineering issue. I will touch briefly upon that following. So now you may, of course, ask yourself, how does the water uptake occurs? Or where does the water go to in this MOF pores? And to answer that question and also show you another aspect, I will come to a MOF here with a muconate linker. So this muconate linker is an extension of a fumarate linker, because it has another double bond, not only one as a fumarate linker. And otherwise, it gives you quite a similar structure again, as you had seen now quite frequently. So these aluminum chains here, tetrahedral chains, and then this square to slightly rhombic channels. And depending on the synthesis condition, actually, we came about second polymorph. So one had a more rhombohedral channel arrangement, and the other a square channel arrangement. Otherwise, the building blocks were exactly the same. One aluminum, one hydroxyl group, and one muconate linker. So the formula did not change. So we have two polymorphs here. What else was different besides the structure? Now, that was the orientation of the hydroxyl groups bridging the aluminum atoms. Here in this Mil-53 muconate polymorph, it was trans-oriented. In the MIP-211 polymorph, we were cis-oriented. So it seems like a small change, but that change has a drastic effect on the region where the water uptake occurs. So the left polymorph, Mil-53, is quite hydrophobic still, apparently, because its water uptake occurs roughly at 0.5 relative pressure, while the MIP-211 polymorph, with the square channels here and the cis orientation, that has much higher hydrophilicity. Its water uptake occurs around 0.3 relative pressure. Now, such a small change, you may wonder, and such a drastic effect. Now, it was with the help of a theoretical chemist that we could answer or understand why that happened, or how did this change in water uptake came about. So the water, when it binds or absorbs in the MOF, has to find some points of higher hydrophilicity. And these are in the aluminum MOFs by bridging hydroxyl groups, which bridge here between the aluminum atoms. So in this Mil-53 muconate polymorph, it can only bridge or accept a hydrogen bond from one hydroxyl group, because in here the hydroxyl groups are trans-oriented. So the next one from the next bridging unit is too far away. Whereas in the MIP-211 polymorph, as you can see here in this scheme or picture, the water group can accept not only a hydroxyl group as an H bond from a hydroxyl group, it can also donate a hydrogen atom to an hydroxyl group. So it at the same time enters in two hydrogen bonds, and thereby it has a much higher binding energy than in the MIL53 gluconate polymorph. And that gives this morph the much higher hydrophilicity. So this simple or small change of a trans versus cis orientation is the basis here for this difference. So now let's come back to this technological application. And if there are engineers among you as the audience, that addresses now more this engineering aspect. So because as chemists, we can only go so far. And in our collaboration, there were also engineers, and they pointed out a few aspects which we as chemists had also to consider. So in this diagram, which you saw before, I noted that we have to have these four entropies as pointed out here. And especially the heat of adsorption has to be dissipated quickly, because when the framework gets warm or the porous material gets warm, it will counteract the further uptake of water. And of course, the cycling between the working cycle and the regeneration cycle should be done quickly. So time is an issue. Kinetics of adsorption plays a key role here in this technology. And also the temperatures are of course important. So we have, of course, to draw heat of evaporation from a working fluid, from water. So in order to do that, this temperature to which we cool this chilled water circuit should be as low as possible, because that is what gives us then the cooling for the device, let's say a room or a building and so. Then we have the recooling cycle, where the circuit where the heat of adsorption is dissipated to. And so here we should be able to dissipate heat which is as high as possible. Of course, the MOF should still then take up water at this temperature. And then we have to regenerate the material. And for that, we have to bring in heat of desorption, which of course should be as low as possible. So these are now engineering constraints which have to be taken into consideration. And the material has to try to fulfill these constraints. That means it should work at these temperatures. So here you see a map now which plots the heat rejection temperature, which should be as high as possible. The chilling temperature to which the water circuit is cooled down, which should be as low as possible. And still the material should have a high water uptake, which is the white triangle here, which plots the uptake capacity in gram per gram. So now this has to be optimized. So for example, let's say if the heat rejection should be done at 30 degrees centigrade, you would have to go, or could have at least, or at the lowest, have a chilling temperature of 10 degrees centigrade to be still in this white triangle here. And if you go to 36 degrees centigrade for the heat rejection, because I said it should be as high as possible, then the chilling temperature could only be around, let's say, 15 or above 14 degrees centigrade. So it could not go down as low as would be perhaps desirable, so that the uptake is still as high as possible. So this is engineering-wise map of the constraints which should be fulfilled by this material. Actually, the material from which this curve or this plot is made from is Cow10H with the isophthalate linker, which I had shown to you before. with its uptake capacity and uptake curve. So now a second issue for the engineers. So drawn in here in these boxes where the sorption material is either dry or wet are shown these pipes, you could say. So this is now an issue which affects the kinetics. So in this little schematic photograph or infrared image, I had depicted two glass bulbs. Now, such a glass flask is, of course, no good in terms of outer surface area for heat dissipation, because a sphere has a low surface area, outer surface area, compared to its volume. So this was only a scheme. Now, for this technology, you have to have absorption material in close contact to a metal surface from which the heat of adsorption or the heat of desorption is dissipated or brought in. So that means we have to have a real heat exchanger, which then perhaps is filled with a MOF, or the MOF is then brought into this in between the lamellas of this heat exchanger, so that we have a device which dissipates the heat of adsorption and brings back in the heat of desorption as quickly as possible to at the best thin layer of porous material only. So that is how it could be translated into a real world. Here is a thin coiled heat exchanger. The blue part or the blue cover is a MOF, which is a copper MOF, so that it looks better, which was brought onto these metal fins here. And here you see this heat exchanger, which I just showed to you again. And now you see some white stuff in between these lamellas, and that is a MOF. So I will come to that second part here again. But before I do so, I point out that there are different possibilities how to combine a porous material, or in our case, MOF, with the surface area of a heat exchanger or a metal surface. So the black bars, the thick black bars are the metal surface, and the porous material are the gray balls or the gray spheres. You can just put them in between, and the disadvantage then is that the heat which is dissipated from each of these spheres has to go a long way to reach the metal surface from which it is further dissipated to the environment. So if you glue the spheres onto the metal surface, this heat dissipation is a little bit more effective. And if you make the spheres now smaller, let's say into nanoparticles, then you can make this heat dissipation even more effective by having a more inherent contact with the metal surface. And the best would be if you transform the metal surface partially into your metal-containing porous material. So because this way, then you have a direct contact, because this metal coordination network or MOF will be grown then directly from the metal surface. So from left to right, you have an increasing heat transfer. That means an increasing adsorption rate and an increasing cooling power. So we start with the left one because it's most simple. And as chemists, we cannot do everything. So we just showed that schematically it is possible to have a MOF made in spheres and then brought into in between the lamellas of a heat exchanger. So in order to transform a MOF into spheres of 2 millimeter, we have to bring in a polymer, an organic polymer, but only to a weight percentage of 10%, which then binds the MOF powder into stable or mechanically stable spheres. So these spheres you see down here again. Here you see a heat exchanger, and then in between the lamellas here of this heat exchanger, we can put the spheres. From below there is a net so that they don't fall through. And then this was investigated in terms of its water uptake and release and its capacity. And that is shown here. So mass uptake in terms of water over time is rather quick. And then the cooling power, which is about 350 to 400 watts per kilogram of adsorbent. So it is only the kilogram of MOF in this case. It's not the whole heat exchanger. So that is a little bit better than silica gel grains, which would be could be prepared similarly and brought also into this heat exchanger. You also see that what I told you before, that this uptake or until the MOF is fully filled doesn't take much time. So here it's about, let's say 500 seconds until we reach about 60% of filling. And one would not run this process to full equilibrium or to full uptake. That's not economical. So after, let's say, 500 seconds, one could turn this process around already. So let's go down to the binder coating, which is more efficient and also a bit more complicated. So for that process, we could use, let's say, a surface coating process, a spray coating process, or a dip coating process. For the actual example, we used the dip coating process, where this heat exchanger was coated, was dipped with slurry, which contained the MOF. So that then gave you this image, which you saw before, where now the heat exchanger is filled with a white material. And that was, in this case here, about 500 grams of aluminum fumarate and some additional binder with a weight percentage of 10% coated in this heat exchanger. So now measuring again its cooling capacity. So it reaches a capacity here of 2,900 watts at the very beginning. And then due to a filling, which occurs quite quickly, the MOF is in a very fine state here in terms of grain-wise. And it drops down now already within less than 100 seconds to half of it. But again, that shows how quick the filling occurs and how quick the cooling capacity or cooling power is generated. And after 100 seconds, or maybe 150 seconds, one would be able to turn the process around to regenerate and then go to the working cycle again. So the overall cooling power then is 1,400 watts per kilogram, and 1,000 watt would be considered here after a half cycle time of 74 seconds that this value is reached. So that shows you that these type of MOFs in real heat exchangers work and could be developed further into the already existing technologies. And before I now come to my final conclusions, let me point out some other aspects which go along with water absorption in MOFs, and that is primarily nowadays from the group of Omayagi, water harvesting. So I only show you this one single picture here, that MOFs, as they can take up water and are stable and so on, and especially can take up water at low humidity, as I have shown. So at a low relative humidity of less than 0.3. So, and this low humidity is, for example, even existing in desert climates. So especially at night. So at night, you have a little bit of higher humidity than daytime. So you can then absorb the water at night in the MOF and release it again during the daytime when you have the sun giving you the heat of desorption. And thereby you can harvest water in an environment where you have no natural water, or you have problems with obtaining clean natural water. And so the work of Yagi points that out, and some other groups have done also research in this field. I will not comment on that any further. And so now to summarize, what I have told you. I've shown to you that MOFs could be used in the existing technology where water uptake plays a role, and that technology was water adsorption for heat transformation in air conditioning devices. And it's not only to manufacture a MOF. Once you come to a real technology, the engineers will tell you that other aspects are important, such as sorption kinetics, thermal conductivity, in this case here to dissipate the heat. Anti-fouling is an issue once you have an open environment application. You, of course, need a large-scale synthesis for the MOFs, and the synthesis should be economical. The metals should be non-toxic, and the list goes on. So, that is some of that still remains to be solved. And with that, I summarized yet some other aspects of the heat of desorption, evaporation, and so on, which go together with the heat transformation application. So one could also, of course, use other adsorbents. MOFs come only in that field because of their high porosity and economic, to make the process perhaps more economical. But then shaping is an issue. The adsorbent, I pointed it out briefly, could also be replaced. I have used water here only, or talked about water only, but ethanol, methanol may also be a possibility. So with that, I'm now finally at the end. I have to thank my colleague from the engineering side, Dr. Stefan Henninger, with whom I made the investigations concerning cycling and the heat exchanger and so on, and the colleagues who also contributed with their MOFs and expertise, and the people in my group who over the years worked in that field, and the money who came from federal ministries in Germany on economics and technology and education and research. And I thank you very much for your very kind attention. Thank you.
Thank you very much for a very interesting lecture concerning application of MOFs and using energy efficient system for conditioners. Dear colleagues, do you have questions to our lecture?
Yeah, please just pose your question, because I can only see some of you, and so I could not say who should be first. But maybe Valentin, you have better impression who raises maybe his hand or wants to ask something.
Okay. My question very simple. As far as I know, MOFs, the big problem of MOFs, it's a reproducibility and scaling up of synthesis for real commercial applications. What do you think about real commercial application of MOFs for such systems? Scaling up,
okay,
reproducibility, exactly.
So that is certainly correct when one tries to scale up MOFs on a laboratory scale, because there are so many parameters. Everybody, I mean, as in any synthesis, any chemical synthesis, you have temperature, time, pH, ratio of reactants, and so on and so on. But the company BASF or BASF has quite early on, so starting in the early 2000 years, scaled up many MOFs, not through the typical lab synthesis, but using electrochemical routes. So they used an anodic oxidation of metal. The linker would be in solution, and from there, the MOF would be then generated. And according to them, they were able to manufacture MOFs on the ton scale, and they also distributed actually samples around the world. And what was maybe a drawback is that these MOFs would not reach the same high surface area as the small scale MOFs had. But that may not be so much an issue as long as the MOF is reproducibly available and stable, and it works. So there is a saying from BASF: if you have a MOF where you have really a large scale application, we will be able to make it reproducibly. So I wouldn't trust that a company like BASF can make MOFs reproducibly. And by now, there are also some smaller, newly founded companies like MOFGen and others who sell MOFs at least on the kilogram scale. So I think that issue can be solved if you really go to processes which are not batch processes, but are continuous processes. For example, with MOF aluminum fumarate, that can be made under normal ambient condition. At least it does not require high pressure. So it needs a little bit higher temperature, but otherwise it can be synthesized in water and it can be synthesized in a continuous process. And thereby it is easier to have reproducible conditions. So it was a little bit a long answer to your short question. But it's a good question because for a long time it was really an issue.
Yeah, thank you. I have in you information about scaling up of MOF. And my other question is about utilization of MOFs after the using in cooling system.
Okay, yeah, so certainly this is a cycling process. So the MOF would not have to be replaced, at least not frequently, hopefully, because otherwise, if you have to replace it, let's say every year, that would be too expensive because the zeolite and the silica gel, they are very, very stable porous materials over a long time. And yeah, so it is, I don't know how companies deal with the possibility of recycling MOFs. Most likely, I guess that issue has not been addressed yet, as there is up to now no large-scale application of MOFs. That's what I have also mentioned, that MOFs have potential applications, but not, to the best of my knowledge, real large-scale applications. So that means also the issue of recycling or how to deal with MOFs maybe which have poisonous metals like chromium does not come about yet. But I see a question from a person like Roman. I don't know if
yes, we have a question from Roman. Yeah, Roman, please.
Hi.
Hi. Thank you for a nice lecture. I have a couple of questions related to the processing of MOFs and prototyping. My first question is related to MOF activation. So what is the procedure of MOF activation? What do you do to activate it?
Okay. So yeah, okay, maybe let me briefly try to explain to the whole audience what activation means. So the MOF is not porous from its synthesis immediately because solvent or maybe some residual linker is still contained in the pores. That fulfills the role of a so-called pore forming unit. So the solvent is necessary that the pores will form. So you have to bring the solvent out, and what we do is either we apply vacuum together with heat directly if we have a volatile solvent, let's say alcohol, water or so. If we have a low volatile or high boiling solvent like DMF, dimethylformamide, which is also frequently used in MOF synthesis, we use the process of solvent replacement. So when we wash the MOF with, let's say, ethanol or other low boiling solvents, so that the DMF is to a large extent replaced by this other solvent, and thereby, of course, the MOF structure must be retained. And then once we have the low boiling or high volatile solvent in the MOF, then we apply temperature or heat and vacuum to activate the MOF. So we could also, of course, activate directly on the sorption device because the sorption devices have nowadays activation ports where you can heat the sample, and because the MOF, the sorption device has turbomolecular pumps which give a high vacuum, or very good vacuum. The then this vacuum is very efficient. And what we also use as another means of activation, if the MOF is structurally or mechanically not so robust, we use a supercritical drying, so replacing the solvent by CO2 or washing it with CO2 to bring it out carefully without any heat and with no vacuum, and the CO2 then that can be removed when under ambient condition in the very end. So these are the 2 or 3 processes which we use for activation.
Thank you. My second question is related to the pellets what you prepare. You showed very nice process where you combine MOFs and PVA. What was this selection of PVA? It's affected by humidity. It can change mechanical properties. Is it?
You are right, certainly. I mean, that was only a proof of concept, you could say. You are right that in this process here, we use polyvinyl alcohol. I mean, one thing is it's a commodity polymer, very easily available. It has some hydrophilicity, so we could combine it in aqueous dispersion with the MOF crystallites, and that was our why we choose this. And it gave a good also in a way composite with the MOF. So it because the MOF is to some extent hydrophilic on the outer surface, the PVA could stick to it, and we could form these spheres which you see here on the picture with the PVA. We also tried other polymers, of course. Some others also worked, but some didn't. And what was also then important is that the polymer does not block the pores of the MOF. So we had proven through separate investigations that the porosity of the MOF was to a large extent still accessible for the water. It would be no good to have a polymer which really covers or coats the MOF such that it is then no longer, the porosity is no longer accessible. And so in that aspect, polyvinyl alcohol was doing well. But you're very right. So polyvinyl alcohol would also, in a way, with liquid water dissolve again. It would also foul under open air conditions because it's an organic polymer which is prone to colonization by fungi and other microorganisms, which then would induce fouling and degradation. So it's a proof of principle.
And the last question is related to improvement of the prototypes. What you showed, you used only like spray coating, but the main goal would be to increase the surface to volume ratio. Did you try to use electrospinning or 3D printing? Because if you make pellets, it's possible to make a filament, and it would be very nice for prototyping.
You're right. I mean, there are many other ways how to derive at a so-called shaping than what is shown here. It was just the fact that we had nobody with enough expertise, or with really the expertise which you point at, namely electrospinning or 3D printing available at that time, so that we did not follow that up. But you're very well correct that one could envision such methods, which would be maybe more elegant. But still the issue is, of course, to have the contact with metal. So 3D printing maybe goes to a little bit like towards spray coating, but one could certainly develop that further. So it was simply due to the fact we didn't have any partner here, and when as chemists, or the thought is we have gone already a long way being simple synthetic chemists in what we have tried to prove here or to show here. And our interest then changed finally, eventually, and that had to do with some feedback from companies who pointed out to us that we had nice materials, but they would not change their process. Why wouldn't they change their water sorption process for heat transformation? The reason they gave to us was the following. The whole conditions in terms of heat dissipation, temperature, pressure was very well developed for the zeolite and the silica gel they apply in their process. Now, if they put in a new material, they would have to go through the conditioning of their process in terms of time, temperature, pressure, once again. And then they said, we don't know, will your material really last 10 years? Can you guarantee it to us? Of course, we cannot. And also the contact, which you see here of a MOF to the metal, that is also a little bit unstable. So after a while, I can tell you, the MOF fell off from the metal plate. So that was the reason why companies were very reluctant to change an existing process with new materials, which were only, let's say, a little better. Because one thing you pointed out was volume. In these devices which you saw, it's not so much the mass which is important, it's the volume. And you are very correct, so maybe you know more about that already. I gather that from your questions, that in such a device, you would have to have the uptake actually, or provide the uptake in gram per volume, not in gram per gram. And MOFs are very lightweight, they have a low density. So if you now calculate the same, what I had shown here to you in gram per volume, the MOFs would be no better than the zeolite and the silica gel. So thank you for these questions, which in a way allowed me to give some comments. But that's life. So yeah, I guess only in the very end you discover as a chemist that companies want to have more than you actually can give to them.
Thank you.
Thank you very much for very interesting answers. So, dear colleagues, maybe other questions? I don't see any hands at the moment.
That was already, actually, Roman asked 3 questions. I mean, maybe may I ask Roman, do you have any further knowledge on that process? Because your questions really showed a great insight.
We are from University of Latvia. Here we are like 2 people, me and my colleague, Dr. Artis Kinens. So we joined Valentin because his team and he organizes nice lectures, and we are doing prototyping also. One of the activities is 3D printing and electrospinning. And I hope to discuss with Valentin possibility of collaboration between our groups, because like I'm originally from Ukraine, and now we're trying to keep in touch with Ukraine, and we are also open for prototyping and for activities with MOFs.
Okay, I see. Thank you.
Yes, and we also would like to start our activities in the field of MOF in Ukraine, in Kharkiv. Therefore, it will be also a collaboration between several parts, not only Germany, Latvia, Ukraine, and other as well. Yes, and Roman, we will discuss, of course, our collaboration maybe next week.
Yes. We are waiting for that. So that's why I asked artists to join us, because we are interdisciplinary team. We are physics, chemistry, and engineering, and we are open for collaboration. So we have a lot of progress with 3D printing. We print tablets now for pharmacy. So like feel free to contact us. It's no problem. So and we would be happy to collaborate with Ukraine. Yes, as that's now that's a good opportunity to go from boards to activities.
Okay.
Thank you.
Thank you. So I don't see more questions. And
Okay, neither do I. Yeah.
yes.
Okay, but thank you again for this, for listening and for this discussion. Yeah.
And thank you again for your time and very interesting lecture.
You're very welcome. Yeah, it's the least I could do. You have much more difficult times in Kharkiv, especially, or the other parts of Ukraine. And I wish you all the best for your future. And I hope to see you again in some better times when you visit Germany, maybe again. Yeah.
Yeah, in Düsseldorf.
Cool.
I think yes.
Yeah.
Thank you.
Okay. So thank you.
Yes.
All right.